Welcome to this video on the topic of networks. In this video, we're going to have a look at how we can go about discovering the minimum spanning tree within a connected network. To do this, we're going to look at two algorithms. The first one being Prim's algorithm, and the second algorithm being Kruskal's algorithm. But before we look at the algorithms, let's review the idea of a spanning tree. A spanning tree is a collection of connected paths which, when observed as a whole, do not contain any circuits. What you can see in the graph over here is a spanning tree. So although it's a connected network and there are multiple ways in which we can connect all these nodes together, denoted in purple here is the spanning tree, or a spanning tree, for this particular network. Notice how all of the nodes are included in the network, however they're included in such a way that there are no circuits. So a circuit being if we saw something of the likes of F connected to B like this. This would create a circuit, but we don't have that for spanning trees. Now, a minimum spanning tree within a connected network is a spanning tree that connects all nodes via the lowest weighted paths. To be able to discover the minimum spanning tree, there are two algorithms you can use. The first one we're going to look at is Prim's algorithm. Now, Prim's algorithm discovers the shortest spanning tree using a top-down approach. Or in other words, whenever we're trying to find the minimum spanning tree using Prim's algorithm, at all times we know all of the nodes and we know all of the connections. We don't have to visit a particular node and look outwards, rather we can just look down on the entire network to see all the information at once. To carry out this algorithm, we have three steps. The first step being, we simply pick any node to start at. It doesn't matter which node, we can just pick it arbitrarily. In this case, I'm going to pick node A. For step 2, from any node currently within the minimum spanning tree, branch to the nearest lowest edge weight node that is not within the tree. So effectively looking at this, starting from A, we're going to pick the edge which has the lowest weight. Now all of the edges connected to node A here, we have this one connecting to C, which is 9, one to D, which is 5, one to F, which is 10, and one to B, which is 8. Due to the way in which the algorithm is written, we have to pick the lowest weighted, that being the one with 5. So I'm going to branch outwards to D, like so. And as a result, we now have a path within our network connecting A and D. So at this point in time, this is our minimum spanning tree. However, it's not complete for this entire network. Going down to step 3, we have, if any nodes are not in the minimum spanning tree, repeat step 2. So we're still missing C, F, B, and E. We don't have a minimum spanning tree for the entire network until we've included all of these nodes. So I'm going to go back to step 2, and it says again, from any node currently within the minimum spanning tree, branch to the nearest lowest edge weight node that is not within the tree. Or in other words, looking from A and D, we're going to look for the least or the lowest connected path. So in our case, we've got 8, 9, 8, 7, 10. We're going to pick the lowest one, in which case it's going to be 7. Branching outwards. Alright, step 3. We're not complete yet, so we go back to step 2. Now looking outwards from all of our nodes currently within this spanning tree, we have to look for the least weighted edge. We have a 9, 8, 10, 10, 9, 8, 11. Now we have a tie between the two 8s here. We can pick either 8 we want, it doesn't matter. In this case I'm going to go for the one on the left. So I'm going to branch outwards to C. C is now included in our minimum spanning tree. Moving back, we still have B and E outstanding, so we're going to repeat step 2. We're going to look at all of the branches or all of the edges, for which we see that 8 is the lowest branch. So we're going to branch to B, go to 3, go back to step 2, and we connect E via this edge here. And thus we've been able to create, or we have been able to discover, our minimum spanning tree for this particular connected network here. Now if this is the graph showing our minimum spanning tree, we're also able to calculate the length of our minimum spanning tree. the length of the minimum spanning tree is simply going to be the sum of all of the weights on these edges we have. So we have 8, 5, 7, 8, 10. Summing this together, I get a value of 38 units, thus highlighting the length of our minimum spanning tree. So if we think about using this in an application, it could be something like connecting sprinklers on a farm, and the idea is you want to minimize the amount of hosing, so you would use a minimum spanning tree. Alright, moving down. Example B. We'll apply Prim's algorithm on this network over here to be able to discover the minimum spanning tree. Now at random, I'm simply going to pick whichever node I want. In my case, I always like starting from node A. Looking outward from node A, I have the option of 4 different edges to travel upon. I have this edge to B at a weighting of 27, this edge to C at a weighting of 12, this edge to D at a weighting of 15, and the edge to F at a weighting of 16. Naturally, I pick the lowest weighted edge, which connects to a node that is yet to be introduced into our spanning tree. As a result, I welcome C into the family via this edge here. Okay, now looking outwards, we have A and C within our connected, in our minimum spanning tree. We're going to look across all the extra edges we've added through C. So we've got this one connecting to B at a weighting of 6, this one to D at a weighting of 14, and this one to E at a weighting of 18. The smallest edge, or the lowest weighted edge we can travel upon, is this 6 over here, and it connects to this B, which is not currently a part of the minimum spanning tree, but now it is. Alright, growing outwards, we look at all of the edges that we have available. We have a 16, a 15, a 14, and an 18. Using the edge along 14, we're able to travel to D. D is now a member of our minimum spanning tree. Continuing the pattern, I'm going to move across this edge to 9. And we welcome. Looking down, we have an edge at a weighting of 5. And we connect G. And the final node not within our network is E. We simply pick the pathway, or we pick the edge that's going to have the least weight, in which case it will be 11. So we welcome E into the family. Now that we've discovered the minimum spanning tree for this particular connected network here, let's calculate the length of the spanning tree. For this, once again, we're simply going to identify all of the edges within the minimum spanning tree, and then we're going to connect them together. Performing this calculation, we calculate that the length of our minimum spanning tree is a total of 57 units. So this is how we conduct Prim's algorithm. Starting from a particular node, we branch outwards using the edges or the arcs with the lowest weighting associated with them. We always have to be connected to an edge to be able to branch outwards. Now going down to Kruskal's algorithm, it's very similar to Prim's algorithm. However, we remove one of the restrictions. Within Prim's algorithm, we're only able to branch outwards from nodes that are currently within the minimum spanning tree. With Kruskal's algorithm, we build our minimum spanning tree by connecting smaller parts together. So in Prim's algorithm, we grow it outwards. In Kruskal's, we connect it all together in smaller parts. This is done in 3 steps. The first one being identify the lowest weighting or lowest weighted edge. From there, if the nodes that are connected to that edge are not within the spanning tree, then we're going to add that edge to the spanning tree. If any node is not connected to the spanning tree, repeat step 2. So rather than looking at nodes and branching outwards, what we do is we look at edges and we include them, whether they're going to build our spanning tree. So identifying that, we have to pick the smallest edge within this network, in which case it's going to be this edge over here. This is going to introduce node F and node G into our minimum spanning tree. Alright, moving up, we have to identify the next biggest edge, in which case we have this edge here and we have this edge here. It doesn't matter which one we choose to take. So in this case, I'll pick the one that is the furthest away from the original one we did. You don't have to do it this way, either edge is fine. I just like picking the furthest one away. We introduce A and C into our minimum spanning tree. Alright, now next step, next smallest edge is the edge 3. We introduced E and we introduced D into our minimum spanning tree. Next step is we look for the next smallest edge, in which case it's going to be 4. We introduce this edge. We don't introduce any new nodes, but we connect two smaller parts of the spanning tree together. So E is now connected to G. We identify our next edge, in which case we have a choice of 5, 5, or 5. Now if we introduce this 5 into the network, what we'd end up doing is creating a circuit. So we're not going to do that. Rather, we're going to look at this one and this one. Now it's up to us which one we want to choose. I'm going to use this one here, purely because it makes the minimum spanning tree look a bit fancier. And then finally, we want to introduce B into our network, looking at these edges here and here. So you've got a 6 and an 8. We preference the lowest edge, or the lowest weighted edge, in which case it's 6. And thus we welcome B into our minimum spanning tree. And in doing so, we complete the minimum spanning tree for this entire network. Calculating the cost of this network. Calculating the length of this minimum spanning tree. I'm going to add all of the connected edge weights together. So 6 plus 3 plus 5 plus 3 plus 4 plus 2. This will yield a value of 23. So 23 units in length. And thus we complete our example how we discover the minimum spanning tree within a connected network using Kruskal's algorithm. So in summary, what we set out to do in this particular lesson was we had a look at how we could find the minimum spanning tree within a network, and we achieved this using Prim's algorithm and using Kruskal's algorithm.